Okay, welcome to the second lesson in our series of the first three lessons, which are really an introduction to the cardiovascular system, but it's going to be they're focused on the heart. Okay, so this is a cardiac. These are cardiac myocytes here, This is a myocyte here in between what are called the intercalated discs. Okay. And the intercalated discs are sort of represented here. They connect cardiac myocytes, okay? They have desmosomes, which are sort of like anchors which hold the cells together at these junctional points. And they contain gap junctions, which are really big channels which allow materials to flow, small organic molecules and ions, most importantly for our purposes, to flow from cell to cell. So because these myocytes are connected together, we say that the heart is a functional syncytium. That means that the cells are connected together in such a way that they kind of, in many ways, act like they are all one big cell. And that is actually true of the heart. Each of these cells does the same thing, and because they're connected together, they sort of act like one big cell, so that they all contract, and they act like it's one big cell contracting. Okay, that's what we mean by functional syncytium. So these gap junctions, which are part of our intercalated discs, they are what we call electrical synapses, and they allow bidirectional movement of ions. They are made up of connexins. As I said, they're very large. They allow electrical communication between the myocytes by allowing ions to flow in between. And they also allow small organic molecules like nutrients and metabolites to get through. Okay? Because these are there, these individual myocytes sort of act together like they're one big myocyte. All right? There is no synaptic delay in an electrical synapse. So synapses are points of communication between cells where one cell will cause another one to be stimulated. Typically, we'll talk we'll talk about that in a great deal of detail in later lessons. But the reason why that's important here is because the existence of these gap junctions allows the spread of the action potential through the heart, which we're going to introduce in a moment. What that means is that, I'm a myocyte. My sister is over here. My brother is over here. Okay? When my sister depolarizes and there's an action potential propagating down her membrane, through her membrane, that action potential will hit these gap junctions at the intercalated disc. Because those gap junctions allow her to communicate with me through the ions, that action potential is transmitted from her to me, and she stimulates me, and an action potential fires in me, and it propagates across me from left to right. And when it hits my intercalated discs on my right side, that's my communication with my brother. Because those gap junctions are there, the action potential propagates to my brother, and it propagates on and on from there. That is the way that action potentials propagate through the heart. And they propagate from cell to cell across these intercalated discs because these gap junctions are there, and that is really the point of bringing them up here. So this is a typical ventricular action potential, which is going to propagate from cell to cell through the heart. And what we mean by an action potential, this is a transmembrane potential measurement. Typically, it is the voltage outside the cell relative to the voltage, the voltage inside the cell relative to the voltage outside the cell. Okay? So those voltages are different because the ion concentrations are very, very slightly different on the different sides of the membrane. So we have a resting potential in a myocyte of about minus 90 millivolts, okay? And what that means is that there are slightly more negative ions on the inside of the membrane of this cell, slightly more positive ions on the outside of the membrane. The inside is negative relative to the outside, so we say that there's a potential difference across that membrane. And we say it's a negative potential difference because it's more negative on the inside, okay? The resting potential about minus 90 millivolts, and that increases to about plus 20 at the peak of this action potential. That means that at the peak, the inside is positive relative to the outside, which means it has more positive charges on the inside than on the outside, okay? For those of you who don't know, this is due to sodium influx. We will talk about that in a great deal of detail. For now, just know that the voltage goes up and that the duration is about 300 milliseconds. That is much larger than a typical skeletal muscle or nerve cell, okay? These action potentials are larger in cardiac myocytes, so we will talk in great detail about why that is. Again, these propagate via gap junctions from cell to cell through the heart. We'll talk about how that works in a moment. And the entire purpose of this action potential in a cardiac myocyte is to open calcium channels. They open in response to voltage. So when the voltage goes up, calcium channels go up. Calcium flows into the cell and causes contraction, and it is also released from an intracellular organelle called the sarcoplasmic reticulum into the cytosol. And the increase in calcium due to these two things causes the cell to contract. High calcium, increased force of contraction, and higher stroke volume. Okay, and that brings us to the Wigner's diagram, which will be the topic of the next video, which I'm going to go through. Thank you for your attention.